the stream. So today, what I'm planning on doing is this kind of assignment thing. So someone sent me this because he needed some help. And I might just try to do that. So let's quickly read this line by line. I'm gonna open Synergy. Excuse me, sorry. So for this assignment, we will implement a basic neural network. The notation that is used is in Alpigin to help you understand the correlation between a single perceptron and the linear discriminator function, and to understand the derivatives that are the basis of backpropagation. However, it does not contain enough information to build like a complete multi-layer perceptron. All right. For this, we will use different notation. The benefit is that it's complete, so translating it to data operations is relatively straightforward. Also, the notation tends itself well for matrix multiplications. All right. Sure. Okay, I kind of want to split this, which is, I think, Control Shift minus, Command Shift minus. Nope. All right. The perceptron. So what is the perceptron? So let's start by zooming in on the parameters for just one node in the neural network. So and there are many different types of activation functions. That's true, such as sigmoid, logistic, ReLU, etc. But the sigmoid activation is a classic and most common type, which is not true actually. I think the most common type is a ReLU or a leaky ReLU. That's because it achieves a very good classification, but the derivative is extremely simple. So especially in deep networks, the most common type is not a sigmoid one, but a ReLU, like a leaky ReLU. If you use this activation function for a single node perceptron, the combined equations will correspond to the logistic regression. Watch these two videos for the idea behind logistic regression, or why the sigmoid function is used for this. So let's open up these two. If they want to, I think it's Andrew. Yeah, I'm not gonna go through these actually. But logistic regression, 7 minutes. 7 minutes is not. It's not too long. Maybe I'll watch them when we have the time. All right. The sigmoid function is defined as gx equals 1 over 1 plus e to the minus x. Now write the function sigmoid func that can take a single value or even an array of values and compute sigmoid function for each. Hint, numpy, hint. NumPy built-in functions and basic arithmetics work both on the numpys and the single values. So, all right. So let's see if we. So there is already something here, but let's see if we agree with this actually. So we have to write a function sigmoid func. It takes in an argument x, and it returns 1 over 1 plus mpx minus minus x. Sure, but I'm gonna make this. So I'm thinking of making this like point. I'm not sure if that actually matters. So let's try run this. There's a typo there. There's a typo. 1 over small x. Let's call sigmoid function, and let's call it a 1. How do I run a function and then stay in that cell? That's a good question. Let's see. Help. Keyboard shortcuts. Run. Run selected cell. So shift, command. Shift enter is invalid syntax. Wait a second. I'm doing something really stupid. Import numpy. Define Sigmoid function takes an argument x. So returns. Isn't it return? All right. But so let's say we return 0. That also works. Cool. But so let's test it, I guess. So MP array, so sigmoid func MP array. How do you define an array actually? MP array. Can I take 2 tabs? Keep them open at the same time. NP array, 1, 2, 3. All right, so this should work. You input a list. 1, 2, 3. Okay, that works. Print. All right, so that both works. Fine. Testing. All right, so adding a bias node. So I want to zoom in a bit actually here, slightly. Another one? Yeah, that's good. So all right, so that's done. We can add a check mark actually behind it, I think. Does that work? It does. All right, so we read the perceptron as well. So check mark over there. All right, we also did this already, so we can add a check mark there as well. All right. Okay. So I guess we're done with that. Add a bias node. So the model for a logistic regression is given by yt is equal to 1 over 1 plus e to the minus linear combination plus a bias. Can compute every yt value for some matrix of x values. However, there's an alternative. If we expand the matrix x with the column of ones, just like polynomial regression D matrix, then the equation simplifies. All right. And the model for a single perceptron node, wait a second. I'm missing some data over here. Mm-hmm. Given that your Sigmoid func can also handle array inputs, transforming this array into an array of a sigmoid... Shit, I have to stop clicking. So, given that your sigmoid function can also handle array inputs, transforming this into an array of sigmoid functions should also just be a single function call. Doing each of the functions efficiently is the key component. Write a function add bias, which takes a matrix of x values and returns the same matrix with the columns of 1. Okay, that should not be too difficult. So there is already something here. NPC one's shape x not and appends x. Okay, so let's add constant numpy to matrix. How do you add a scalar? What is np.c? NumPy c. What does c underscore mean? C underscore. Some kind of concatenation. Use IPython's question mark syntax to know more. So let's type C underscore question mark. Object C not found. So let's type np.c. Ooh. In particular, arrays will be stacked along their last axis after being upgraded. So if you have C 1, 2, 3 and X 4, 5, 6, 1, 2, 3, 0, 0. Okay. So add along the second axis. Okay. So there's already something here, but let's write it anyway. So define a function, add bias, takes the matrix values of x. Let's actually, and it returns the same matrix. So it appends that numpy 1s with the same shape, same amount of rows of x and x. Okay, so let's test it. Add bias, print, add bias, np random. Isn't there like a rand? And then maybe 2 times 2 or something? Okay. Okay. Yeah. Yeah. So and then this shape is of course 2 by 3. Okay, that's cool. And that works. Okay, so we did that. We added the bias node. Add bias node. Okie dokie. Oh wait, 1 second. Of course, gotta get that lightning game on point. There we are. So the lightning's better now. Okay, so that's the bias node. Then expanding to a single layer of nodes. Let's see. Ooh. There are some things that are... I'm missing some files over here. Let me see. Until now, we considered only... Until now, we have considered only individual outputs, but neural networks are built from layers of these nodes, right? Each of these layers consists of a combination. Using multiple nodes, it's possible to classify multiple classes. See video below, I'm not going to click it. As each of these sigmoid nodes will need a set of weights based on their inputs, the weights for a single layer will now be a matrix called theta 0. So let's keep a small list somewhere. Maybe here or in real life. Now let's keep a list of symbols. So let's say how do we do LaTeX? It's just begin a line. Just itemize. Begin, itemize, end itemize? I don't think so. I think this is gonna throw an error, but yes, it is. So, oh wait, no, actually, IPython has lists in general. So if we put this into code, markdown, and then we type like star. So theta naught is the weights of the first layer. So from the input to the output or first hidden layer. All right. Okay. Then we will start with a single layer, so no hidden layers, but in a complete network, this matrix is indexed with theta subscript j ki. So the weight from node I in layer j to the kth node in layer j. Note, this indexing might seem counterintuitive, which it is in my opinion, but it is convention for a reason, which we will see later. So let's write that down, because that is quite important actually, because I already helped that friend a while ago, but I actually misunderstood that because we didn't do this part. So this is the weight from the ith node in layer j to the kth node in layer j plus 1. So this is important. This is important for reasons we will see, I guess. But it's important because like it's like exactly opposite of what I would write down, so we have to keep that in mind. All right. So for now, we will build a single layer network, which means we will only need to define. I keep clicking. which we will only need to define theta 0. Consider the example image here with the single layer network. It has 3 input nodes, 1, 2, 3, and a bias node, and 3 output nodes. It can learn to distinguish 3 classes based on 3 inputs. So the matrix, yeah, so we can actually, I think I can quickly draw up a picture. I mean, we're gonna draw anyway. So let's rev up Photoshop. Should I get out my tablet? Yeah, I'll get out my tablet. Just give me a second. All right, and there she is. My beautiful tablet. There we are. Because, like, I think that like drawing is such a nice way of visualizing stuff. So let's see what we can do over here. Let's make a new document. Say 1,000 by 1,000. Nah, let's make it like 500 by. All right, 1,000. No, let's make it like 800 by 1,000. It seems about right. It's probably gonna be very small. That's fine. We can zoom in. Sorry, excuse me so much. So let's make it a nice black. So the layer that we're gonna work with right now is like 1, 2, 3. It has a bias, and it has 1, 2, and 3, which is like, so this is the input, and this is like the output. So it has 9. And now we have to be very careful, because this is exactly, so these weights, I want to make it in green, like, so these weights are theta naught, right? But this little weight is theta naught 1, 1. This one is theta naught 1, 2. This one is theta naught 1, 3. Because the notation in this particular assignment is exactly the other way around. So now I have to kind of think like, is this then also the case? I mean, it has to be the case that they write that down in, so wait, it actually says it here. So, for example, theta naught 3 would describe the weight from the 3rd node in layer 0 to the 0th node in layer 1, which is A naught 1. So we are actually using a 0-based indexing, so we can actually forget about all of this. We can actually erase all of this, because we're going to use 0-based indexing. So theta naught 3 naught, no naught and 3, sorry, naught 3 goes from the 3rd to the 0th, which is this one, right? So let's keep that in mind. Very good. Okay, so I think we did that. So we did the sigmoid function, we did the list of symbols, we did this, expanding. And then we did initialization. So we're working on initialization. So even if we don't know exactly how to compute the corresponding output values, let's start by initializing them in the correct dimensions, right? So we're gonna create a 3x4 a 3x4 matrix. Okay, and now we have to think. Now we have to write this down, right? What is the size? What is the size of theta 0? So the size, like, this is always something that you have to keep in mind. So the size of, like, theta naught, I can't type. Theta naught, the size should be, and now we have to be careful. It should be, like, text times text, where the first text is the number of hidden nodes, and this is the dimensions of input. So let's keep like, that is something we have to take into account, or keep in the back of our heads, that the size should be hidden nodes times input. Okay. So that's exactly the other way around. So when creating a neural network, it's important to use random starting values for the weights. This has to do with the fact that we will again use a partial derivative to find optimal values for the model parameters. And we want to find different derivative values for different nodes. All right. So for now, let's just create a matrix with some random starting values so we can begin computing outputs for one layer. So write the function one layer init, which takes the number of input and output nodes and returns a matrix of weights in the correct bias. Each weight should be randomly initialized using a uniform distribution. All right. So, okay, so there's already something here, but let's write it ourselves. So we gotta write a function, which is oh my god. I keep clicking and editing. So the function is def one layer init, and it takes the number of input nodes. How to do that? Number input nodes? Is it like, it says input size takes the number of input and output nodes? Yeah, okay, so input size, output size. Yeah. Input size, output size. Okay, I agree. And returns a matrix. Maybe we should actually write like a docstring. Takes the number of input and output nodes and returns a matrix of weights of the correct dimensions. Is this capped at 80? It's not capped at 80. Set text width equals 80. Okay, that's quite annoying. All right, so can I do that in Jupyter? Maybe something like 80 call Jupyter. Okay, so we return the matrix of weights. Don't forget to add the bias. So where is the bias? Input size plus 1. Input size plus 1. Yeah, so we can just return the NP random uniform. My computer is slowing down significantly. I'm not sure what's happening, but all right. Yeah, so that's minus 0.3, plus 0.3. And the size, of course, you don't pad these, but you do pad the next ones. It is output size by input size plus 1, which is true. So output size, input size plus 1. And I'm not sure if I want to add spaces here. I don't think so. I'm just going to add a quick comma, so plus 1 bias, of course. And then we want to test it. All right, so let's test this. I actually want to get rid of most of the text here, but like, there's quite a lot of text. Okay, so let's test it. Wait a second. I'm going too fast. So wait. So all right, so we're here now. So one layer in it gives a 4x4, right? 1, 2, 3. Wait, so this is the input size, output size, and the matrix then is 3x4. But because we add the bias, we get, of course, a 3x5. Okay. So that makes sense. Yeah. Okay, so now we have the initialization of the weights done as well. So check mark. Let's do that. So let's combine these pieces. This model will not be able to learn. Just compute the weights given some input and a matrix of weights. I don't understand why it should not be able to learn, because I think it honestly it should be able, because we have weights, right? And like weights are the parameters that make the model learn, so to speak, right? However, you already have a bit of an idea of what it could look like for a one-layer network, but here we will work on the complete multi-layer version. So in order to get a picture, some sense of the final picture, watch these two videos. I'm not going to do that. So for the multi-layer case, the outputs from one layer just become the inputs of the next layer, completing the system of equations. Each activation at the input layer consists of a bias term and the values for each of the inputs. Okay. The combined input for each next node in layer j+1 is the sum of the activations from the previous layer multiplied by their respective weights. Okay, so now we have to be kind of careful. So I wanna write out this math because the dimensions matter, right? So imagine that we have a naught, which is like 1, x1, x2. So that's a two-layer network. Then we want to multiply that by the weights. Let's see over here. If Photoshop decides to cooperate. But now we have to be careful. We have to be extremely careful about the weights, right? Like, so this is a two-layer neural network, and so I'm gonna the combined input for each next node. So A naught is a matrix, which is A naught is the input variable. So A naught is so A naught is 0 is n times features. I'm gonna write that down. That's important. So A naught, which is the input data, size should be n times, and then we have like features plus 1. Where the, right? So we have n observations. Okay. But, okay, so now the question is, how does this exactly work out? Because these are the, so these are then the new activations, which can be used as input for the next. So this also should be a matrix, which is n times something. This is done element-wise, which is an element-wise operation, but this thing has to work out properly. So let's see if we can write down here what theta naught looks like. So let's have a, so we have a two-layer, so this is the bias, this is 1, this is x1, this is x2, and let's say we have two hidden nodes. So we have this weight, this weight, this weight, this weight, and this weight, and this weight. And now we have to be kind of careful, which I'm going to indicate using color coding. So we know for sure that theta naught should be hidden nodes times input, right? And the input is 3, and we have two hidden nodes, so we have a 2 by 3 matrix. So this should be 2 by 3. This is 1 by 3. 2 by 3 is hidden. Okay, so then we have theta. I'm gonna theta naught 0, 0. Theta naught 1, 0. Theta naught 0, 1. Theta naught 0, 2. Theta naught 1, 1. Theta naught 1, 2. Okay. And now let's see, like, what is this first thing over here? So this thing goes from the 0th to 0th, so that's this thing. Then the next thing is this thing, which goes from 1 to 0. And then finally, well, not finally, but so this thing goes from 0 to 1. So in theta, each column corresponds to the input node, so to speak. And each row corresponds to the output node, which admittedly makes a lot of sense when you look at the dimensions. Okay, so now we have that in order. We're gonna have to look at the formulation of this formula. So zk j plus 1, where z is just the numbers that you're gonna plug in here. So eventually like these are going to be numbers, right? These are going to be new inputs, but before you do that, you need to take the linear combination of the inputs times the weights, which we call z. So zk j plus 1, if Photoshop allows me to write. equals L A I J theta Ki. So assuming that this refers to the row, I'm kind of afraid we're gonna have to work a bit more on this, because I'm kind of confused if we write AI, and then AI is supposedly a single. So in this context, if we use A0, AI is of course a single number. But if we consider A0 to be a matrix, which is n by d, then of course AI is a row. But assuming we are not generalizing and we're sticking with a single observation, AI is but a number. So let's see what we can do with that number. So we had the formula here, which is sum over, I forgot what, Aij theta Kij sum over k, sum over I. So this is equal to Z Kj plus 1. So so Z, ideally, right, Z should be 1 by 2, ideally. So Zj or Z, I guess. So that's not, it's Z1. Should be 1 by 2, so Z1, Z2. So let's see if that makes any sense in this context. So let's actually write that out for Z1, I guess. So we sum over all I. So I goes from, well, 0 to 1 to 2. So 1, 2, 3. AI is but a number. So AI is a number. And theta Kij is also a number. So what do we get? We get 1 plus, no wait, sorry. We get 1. We get 1, so this thing, times theta K, shit, we have to start at 0, of course. So 0, so we keep the K, so this thing is equal to this thing, right? So we keep the, we keep 0 fixed here. So if we, okay, so we keep 0 fixed here, and then for the second one we keep that fixed, so we do like this, times this, this times this, this times this. And then we add that. Okay. Okay, that makes a lot of sense. So I'm gonna, so that's just the element wise and then the sum. Okay, so instead of doing actually like, instead of doing matrix multiplications, we're doing element wise multiplications here. That is why we use the weird kind of notations. So I'm gonna make a quick, Z is then, what is it? 1 times, and then we have a text, number of hidden nodes, or n times that, I guess. Note that in calculating Z, we use element-wise multiplication of A and theta. And then you sum over that. So we can do that, actually. That should not be too difficult. So, and then we take that. Okay, so we can put a check mark. We can put a check mark here. Check mark. All right. Wait a second. An important thing to note is that all these equations are for a single row input value of x. So they just compute the... Oh, thank you so much for subbing. I kind of... My sound is off. Wait, I'm gonna hit up Streamlabs. If my synergy... Okay, so I'm gonna open up Streamlabs real quick. Thank you for subbing. I really appreciate it. It means a lot to me. You're my 69th sub. So congratulations on that. We're almost breaking 70 actually. All right, so let's see. We have DSP is love. Thank you so much for following. I appreciate it. Thank you, dude. All right. So where were we? So an important thing to know is that for a single row, right? Whatever the dimensions, in order to make your code more efficient, you should write all these functions to compute your steps on an entire data matrix. So the data matrix X in general, I always use n for n rows, but so it often can be written as a matrix multiplication. This does not only apply to the functions directly below, but to all the following. The code to write the function should actually be shorter and more efficient. So take the time to think about how you could avoid writing loops. Drawing the dimensions of the matrices might help, which is something you should always do. Yes. Yeah, so I'm kind of thinking like, how do you now, if you have multiple rows of A, how would you do that in terms of like I would use a matrix multiplication, I guess. This is like this times this, this times this, this times this is like literally a matrix multiplication if you just transpose it. So imagine that you have like 1 x1 x2, and if we now somehow manage to transpose this thing, so it becomes a 3, so we have 0 0, you have 0 1 0 0 2, and then you have 0 1 0 1 1 and 1 2. This is a 1 by 3, this is a 3 by 2, so you get a 1 by 2, which is exactly what you want, right? So and if it's not like, if it's an n matrix, you get like an n by 2, which is also exactly what you want. So write a general function called compute layer, which takes in a matrix of aj, where each row represents the activations for a different data sample, and matrix data j, defining the connections between and return matrix j plus 1. Try and write this as next, write the function one layer output. Okay, so let's first focus on compute layer. So we take an A. Alright, so there's already something here, but let's write it ourselves anyway. So write a function. Oops. It inserts edit mode when I go up. So define compute layer. It takes in a matrix of A values, where each row and the matrix theta. I'm not sure if I would like use the like underscore j. I don't know. Maybe like, okay, let's just keep the notation for this assignment, I guess. And returns the matrix next aj plus 1. Okay, so we can just return the sigmoid func of yeah, maybe it's nice if you write z, right? I think that's a nice you should not try to be too succinct in Python. So we wanna just take the matrix multiplication, but I forgot how to do matrix multiplication in NumPy. Is it NP dot? I think it is. NP dot. It's a matrix multiplication. But using matmul or A at B is actually preferred. So let's write A at B. So let's do A at NP transpose theta. So let's see if that actually works. So let's run. So A at B is preferred. Why doesn't A at B work? That's a good question. So A at B is matrix multiplication, right? A at B. Why doesn't this work? A and B. Alright, maybe mat multiplication? Warning, this function is... Ooh. Alright, so let's try matmul, I guess. NP matmul. Okay, so that works. Okay, I'm gonna make a quick... Sure, okay. Next, write a function called onLayerOutput, which takes a matrix of X training samples and the matrix weights and returns a matrix of computed outputs. Yeah, so this is just, you take the weights, just name this theta, I guess. Compute layer, which we defined above. Compute layer, let's see. Oh wait, we actually literally defined that. So compute layer, I actually don't like the sound of that. Compute layer. I don't know. Yeah, alright, whatever. So compute layer, we add the bias to the NP array of X, which is not necessary, I think, to force it into an NP array, but... And then we have, so let's call X. Let's take X. We have this beautiful NP array over here. Okay, so this actually does work. No, it doesn't. Do we have to force it? Yeah, so if you don't... Yeah, so if you don't throw in an array, then it errors here. So when you force it to an array, it still doesn't work. Then I messed something up over here. It's a typo. Okay, so you do have to force it to an array. Okay. Alright. So we can put a check mark over there. So let's put a check mark. Alrighty. Compute layer is done. One layer output is done. Multi-layer. Alright, so let's see. In order to work with multi-layer networks, we will need a complete matrix. So write the function nLayerInit, which takes a variational positional parameter for the size of every layer and returns an array of randomly initialized weight matrices of the correct dimensions to connect each layer. N layer init 3, 4 should create a network with 4 inputs and 3 outputs. Should create a network of 2 inputs, 5 and 1 output. Note that you already wrote random. Now write the layer takes a matrix X and an array of matrices. Alright, that's pretty awesome. So there already is a beautiful list comprehension over here. So let's see if we can do better. Or let's see if we can actually first if we can understand it. So let's see. Okay, so imagine we have like a random function. So because I'm honestly like not entirely sure what the star thing does. So for I in TMP, I guess. Oh my god, my computer is foo. And then let's say tuple 111 or alright. Does this work? It does. So but it prints it. It doesn't print it. What does this star do? Parameter specifies that an arbitrary sequence of positional arguments can be provided. I still don't know what it means. Alright. Alright, let's try and see if we can figure out what is being done here. And I mean, if it works, it works, but I still want to understand what's being done. So it's a nice list comprehension. So we have so we force something to an array, NP array, and it starts. So a list starts over here, and then the list ends over there. So that's a big list, and for I in range length of layer sizes -1. Whew, okay, so in all honesty, I am too tired to check whether this is correct, but we can simply check whether it works. So let's do that. It does look very Pythonic. So what have we done here? We have an n layer init, right, which is 2 layers of input, then 2 hidden nodes. Let's draw that. So excuse me. Let's add a bit to the canvas. No wait, we have some space up here. So we have 2 layers and a single output. Then we add the bias. And because we did the silly thing, our weights are hidden by input. So we have 2 by 3. It's the first one. Then we have hidden by input, which is 1 by 3. So I think it does work out. So we have 2 by 3 and a 1 by 3. So that definitely works. Then now write the function n layer output, which takes the matrix X and an array of matrices theta and returns the final output layer. So this is basically the feed forward. This is basically your feed forward step. So yeah, this is actually your feed forward step. Returns the final output layer matrix for that network. So n layer output. So we have the input matrix equals x. For t and theta, x equals 1 layer output input matrix and t. Input matrix theta. Input matrix equals x. Okay, so I'm pretty sure we can do this nicer. Why do we return? We return x. So you put it yeah, okay, so then you return x in the end. I think so we can work on this. We can work on this function, I guess. So this could use some work. But I'm convinced that it does work. So I'm convinced it works. I'm not sure, but I think we can do slightly better. But alright, so everything's up until here, everything's done-ish. So let's put a nice check mark. Alright. Alright, now with all these functions written, it might be good it might be a good time to reflect on what it is that such a network would actually be able to compute. If helpful, blah blah blah. Okay, so these Boolean functions are some of the easiest problems you can compute on neural network, and so they are also great for testing. Create a data matrix X containing all 4 possible pairs 0, 1, and randomly initialize several networks with 2 input and 1 output nodes. So like, so 2 inputs, and then I don't know, like scribble, and then nothing. Compute the output X for each of these and print the results. Since the networks are random, computation results will be random too. This is still useful. Useful is with 1L, I think. To check for errors. Check if the resulting matrix is the right dimension. And check if the values in the matrix are in a sensible range. So we create so this is the input, so these are input features, and here you have 1 layer output. There should be spaces here, I think, at least. I'm not sure. Okay, I'm just gonna leave this where it is. Alright, so blah 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 blah. We want to find the parameters. Blah 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 blah. Logistic regression. Blah blah blah. Sure. Gradient descent. Blah 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 blah. Blah 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 is the first week 1 course. Partial derivative cost function. Blah blah blah. Type of analytical is simple for simple models, not a complex one. In the case of linear regression, initialize. Okay. Yes. Cost function. Gradient descent works exactly like the same more complex models, as long as there's some function to compute and a cost function to optimize. Alright, so okay, so this is the loss function we use. We have y I log h plus It's kind of convoluted. It feels rather convoluted, but we compare the current output to the target output. The video on the topic, if you want to make more regularization term, which is I'm not sure which term is the regularization term, but so let's write the function cost function, which takes a matrix A with the network activations at the output layer. Columns are the different output nodes. So A would be like, if this was already output, this would be A. And the matrix Y of the same dimension, so we can actually put an assertion in here. I think we can do like assert. Would that work? A shape. So let's say A equals 1 or MP array 1 2. A shape. Let's print that. Invalid syntax. Empty assertion. Alright, so 3 by something. So let's say B is MP array 1 1 1. Sure. And now what happens when we do like an assertion, like assert A shape equals B shape? Does that give an so it doesn't error, so that's good. So we can throw an assertion in there for free. Assert A shape equals Y shape. Because why not? I mean, it'll only help us. Unless it throws an error now, which it doesn't. So, and a matrix Y of the same dimensions containing the training targets, so the labels and compute C. So with costs, okay, so there is already something here, and so cost equals not. So we initialize cost for I in range of A shape not. So we're looping over the rows. So for each row slash observation, and then for each call or target label, cost equals okay, np log a I aik plus I'm not sure what the padding should be actually, like 1 minus yik log ak aik. That seems about right. So then we can print the cost function of some random matrices. Sure, we could have just initialized them randomly as well, but that should be fine. So testing. All right, now we're done with that as well. So cost function, sure. If I can type, would be great. So check mark. And I think we can put down a check mark here as well. So gradient descent, learning with one layer. I know we didn't do this exactly yet, but it's nice to have check marks everywhere. So we did the cost function. All right. Yes. And delta terms. All right. So now it's starting to get difficult, I guess. Now we need to take the partial derivative of this cost function for each parameter theta over network. So we can start changing them. The gradients will be computed in 2 separate steps. First, we define a term delta that contains the partial derivatives of the cost functions with respect to the node's input. Okay, so I think I understand what they're gonna do. Like I already noted here that then they're gonna update they're gonna do something. Okay, wait. So let's just read on slowly. First, we define delta that contains the partial derivatives. Okay, which is defined for each ith node in each jth layer. Computing this term separately will make the multi-layer perceptron very much easier to write. For an output layer, when J is the last layer in the network, the delta term is defined as AI minus defined, so EA do not relate to different training samples. Wait a second. This equation is defined for a single sample. The indices do not relate to the different training samples. So yi is the ith target output. So write the function output delta, which takes the complete matrix AJ with all the network activation layers at the, so I'm gonna have to be a bit specific here and write like A are the output activation, which is most likely 1. This should be a matrix of the same dimensions. So again, we could throw an assertion in there for free. So assert A shape equals Y shape. And I think that like output delta 1 should just work. Int has no shape. Okay. So if we have ints, it does throw an error, but we will. So we know that's the case. So we did that very well. So we calculated output delta term. Let's put a check mark. All right. Wait. All right. So now we're walking into some more difficult territory. So computing the weight updates. So with these delta terms computed, we can now take the derivatives with respect to the parameters of the network. So we're taking the derivative of the cost function, which was defined above, with respect to the kith element in the jth layer, which is the summation of delta k j plus 1 to the power of d. No, wait. I'm just going to read the text first. So this is where all the different values for delta k j plus 1, which is most likely going to be a single number in the output layer, right? And ai j, which is, so if we have like, this would be delta k j plus 1, and then these would be alpha j. The sum here is over d is 1 to m, so m training sample. So we are for each element, we are summing over all the observations, our delta values, and the node activations for the dth training sample. So it's not to the power, but it's just a dth training sample. Summing over all these m values will result in the overall gradient. Okay, meaning this will be batch gradient descent. So yeah, it's like batch gradient is not mini batch, it's not stochastic gradient, it's just batch, and then we do like gradient descent. Sure. Okay, so let's see what we have over here. So, okay, write the function weight update, which should compute these values for the weights of one layer. It should return the new value given the old value, activations, the delta next, and the learning rate. All right. So we have the yeah, it should return a new okay, it should return an updated value. So given the old value. So given the activations, delta next, theta j rate, and then so we sum over alright, so I'm not sure if this is correct. Because I think that so we're pretty sure that the so what I think is, so let me make a new let's make this a markdown. So I think that the shape of AJ is equal to M times M times theta nodes so I think that the shape of AJ is M times nodes, so we would have to loop. So if we were to like oh wait, no wait, so he is actually okay, so he's like summing over okay, so okay. This is rather confusing. So let's define a new function. Define weight update. It takes in theta j. Oh, let's keep the order the same. It takes in AJ, delta next, theta j, and a parameter called rate. Then because we sum over for k in range theta j shape, so we sum over each row, then we sum over each column, and then we update theta j ki minus equals rate times dik for delta next AJ. You zip these two. So we keep the delta k fixed. Di and ak, but then why is it not dk? So here we sum over so like NP sum You zip delta next and AJ. So delta next, AJ, you zip those. But do they have the same dimension? I wonder. I'm gonna have to test this. We're gonna have to. So let's get rid of this. Oops. Let's get rid of. Let's get rid of not everything, but. Like, so we're summing, right? We're summing over the observations. Maybe it would be just yeah. Hey Greenie, what's up, man? Nice to have you. Yeah, I'm just making some assignment on neural networks that a friend sent me. Is it? Do you know what I can do about that? Maybe, like, do you know what I can do about that? Because I don't know. Your microphone's cracking. Oh, I turned the gain down. Hopefully it's better. Remove crackle from headset speaker mic. And it's not even a speaker mic. Disconnect and reconnect. I'll try. Okay, so in all honesty, I'm not sure if this is the correct syntax, but like I really have to figure out like what the so it's I'm pretty sure it should be like so for DA in AJ it should be AI and DK, I think. So that does work. Alright, so now we're done with that. In the case of neural layer, weight update will compute all the updated weights in a single step. Here, AJ would refer to A0, the activations, and delta next would be the output. So given some training data, we compute the networks, then compute the deltas, and update the weights. So this is repeated computation, better and better, so slowly decrease. So write the initial one-layer training function, which takes a data set consisting of x and y, weight, some initial, x, y, theta naught. Additionally, it takes iterers to create number of iterations and rate to specify the learning rate. Should perform gradient data set and store the value cost function every step. Should show a plot as well. So function should return the learned values for the weight matrix. Okay, so okay. So does this still work? It does. So we have x, we add the bias, we calculate the output, then we append the cost, which is the output now. We calculate the data delta, and then the data weight updates data rate. Okay. So let's try learning some Boolean values. And does this still work? I should put in like matplotlib inline. All right, so that does work. Okay. Alrighty. Backpropagation. Okay, so all right, so we have arrived at backpropagation, where I tried to help a friend yesterday, and we got stuck exactly here. So I figured out. So I went through the whole document again, and I figured out that they actually define the weights in a very weird way. Um, so they define the weights kind of like in a transpose way, which is something. Oh, I just I just broke the kernel, I guess. Um, so let's see. So up until now, we've only been training single layer networks. The backpropagation algorithm extends this by also computing the error terms of the hidden nodes, thus being able to update multi-layer network weights. So most of the functions you already wrote are still useful in the backpropagation algorithm, only change that there's now a new delta term for the hidden node. So everything we just discussed was the case where this is the input and this is your output immediately. But now we're going to add another hidden node, and we're going to have to calculate the deltas for those hidden nodes as well. But we can do that in this way. So these deltas take the deltas at the next layer and propagate them backwards. So we take the delta from this layer and we propagate them backwards. So that's why it's called backpropagation. The deltas for the output layer and the gradient descent update for the weights remain exactly the same. So for the output layer, so once the deltas at the output layer are computed based on the difference between the outputs and the target, we can compute the deltas for the layer before it. So we can calculate the deltas for the second hidden layer usually. Then we can use those deltas to compute the layers for the to compute deltas for the previous layer, etc., etc., etc. These delta values for the hidden nodes can be used to compute the updates for the weights in exactly the same way as is done for the output node. So let's write the function hidden delta, which computes the matrix delta for one hidden layer, where each row corresponds to deltas of a different training sample. So again, each row is a training sample. So the dimension of delta should be 1 times number of features or hidden nodes. Yes. So it computes for what? Okay, no. It should take as input the activations of that layer. So it should take these activations. It should take the delta values for the next layer, so it takes these values, and it should take the weights for that layer, so it should take these weights. So this is where we got kind of stuck yesterday, but I'm pretty sure we can figure that out. Training. Okay. I'm gonna make a stream marker here, if that works. Whew. All right, so we take in the A, the delta next, and the theta, and then we are going to compute the we're going to compute the delta, and so yeah, so let's copy this and delete it, or at least I don't know. Let's comment it out anyway. We don't want to get influenced too much. Alright. So we wanna we can create delta back, or just delta, I guess. So delta back, maybe just call it delta. We can call that AJ because it has the same shape, so it should technically have the same shape as AJ, namely m times amount of features. Is it? No, wait. No, that's not true. I think delta is the same because we sum over. Wait a second. So here we calculated delta as well. Delta is the size of the input as the inputs that you put in. I'm starting to slowly confuse myself. It computes the matrix of delta values for one hidden layer. Each row corresponds to deltas for different training samples, and each column corresponds to the sample to each of the nodes in the hidden layer. Okay, so yes, it is indeed. So training samples times nodes in the hidden layer. So that is true. It is the same shape as AJ. So then we loop over like every sample. So we loop over all the rows. So for every for now I have to start writing down again. Start writing down stuff. So let's see. We have. We can erase this. So we have like so delta ij equals 1 minus aij sum over k of delta. Was it k plus j plus 1? K theta j k I, if I'm correct. Yeah. So now we have to think like what does it mean that we sum over? Okay, so we are pretty certain that okay. So I think I'm starting to get it. So I think I'm slowly warming up to the idea. So we keep the I fixed. So I'm gonna write it down actually. So like we keep I fixed. That is the training sample. So each row, so to speak. So let's mark down. Alright, so we keep the I fixed. That means that we're going to compute it for different delta 1, delta 2, delta 3, right? So each different training sample. That means that in the theta matrix, which we have down here, we keep the column fixed. So We keep the column fixed, and then we sum over the different rows. Sum over the different rows. Each column. Yeah, because like, okay, yeah, of course, because, let me write that down, because that makes a lot of sense. So, the rows of theta are of size output, which is the same size as delta k plus 1. J plus 1, sorry. Alright, does anyone see that? No, at least I see that. So like, if you have, so you sum over all the k's, which is delta k is the output. So you have the theta matrix here, and then you sum over all the different k's. So delta 1, delta 2, but you keep it fixed, so delta 1, delta 2, delta 3. So then the delta is like this, it's like 1 times something, and you multiply it. But like in most cases, the delta is, oh man, this is actually still, the notation is quite convoluted. So did I write down anywhere about the dimensions of delta? So I think the dimensions of delta are, I think, they are like n times the input size. But I didn't write anything about them, did I? I think we calculated here, so it's n times the input size. So delta is n times the input size. Let's write it down. Wow, our list of symbols is quite far up actually. So here. Alright, so come on. So size of delta is n times hidden nodes. Alright. That's fine. Whew. We are almost getting somewhere. We did that. Did we train the single layer? Yes, we trained the single layer. Backpropagation. Alright, so this was exactly the same formula we got stuck yesterday, but this time we might be able to tackle it, because now we know that AI is a 1 by so wait a second. Yeah, okay, so like the delta, if there are more than one deltas, so we sum over all the deltas. So we sum over all the deltas, so if we have like we sum over all the deltas. let's think about that. So we keep the row, keep I fixed. Okay, I think we're just gonna sum over all the deltas. So let's I wanna I would love to do this in a matrix multiplication way, but I'm too tired, so I'm not even gonna try. But let's start with the second part. So we are looping over the rows so that for every sample we do that, so we get a different DI every sample. And now we sum over, so 4k in range of delta next shape naught. So we sum over the rows of delta. That's muscle memory. We sum over the rows of delta. Then we can call that, I guess, sum. So let's call that sum equals 0. And then we update sum plus equals delta next. NP metal. So I'm pretty sure I'm messing some of the dimensions up here. Ki, but Ki is a number. This is confusing. So we keep the I fixed. Oh man, this notation is really confusing because we want the deltas to have the same shape as AJ. So we do NP multiply. Oh, this is very confusing. So let's see what happens when we do NP multiply. We have NP array, NP array. We have 1, 1, 1, 1, 2, 1, 1, 1, 1. Does this give a matrix NP multiply? So dimensions, NP is not defined? Oh boy. Alright, so let's run all above. Alright. So NP multiply. Oh wait, shit. It should of course be thingy there, thingy there. So this is not I want element-wise multiplication, so what's element-wise multiplication in Python? Good question. Checking my phone. Oh shit. One dead in shooting in Strasbourg, France. That sucks. That's horrible. All right. One second. All right. Whew. Um. Use a multiply, but we used multiply. We used multiply. Okay, I guess we did not. So we're gonna use multiply for that. So element wise. Okay, so I'm gonna try and figure out this formula, and then I'm gonna go to bed because it's getting late already. I want to take a shower. I want to get to bed. So this function, I already checked it. I think it was correct, but we will have to check it. Name hidden delta is not defined. Sure. So that's this function. Yikes. So I'm confident that this is a 1 by features thing. And alpha is also 1 by features. So I'm very confident that this is actually correct. So NP multiply 1 minus this, NP multiply something that is yeah, we only have to be careful that we use like, okay, so that is good. And that's part 1. Then part 2, we return the array, like delta back as an array, where we use delta back append. That is odd. We just want to say delta back I equals part 1 NP multiply part 1 and part 2. Or times, depending on. So this is a 1 by features, but this is also a 1 by features, so the notation is kind of sloppy here. Or I'm making a mistake, of course. And then the only thing that we have to figure out is this part of the formula. Like, so delta, imagine we have any random layer, delta is, if we have any random layer, delta is m m by... Yo, what's up? It's Linton. Thanks. Hello? Better now? Hello. Could you tell me if it's still bad? Oh shit, I should have just plugged it in again. Whew. Okay, so the only thing we have to figure out is what we are looping over in this case. Because delta as a vector is m by the amount of features. So if we are at the output stage, if we're calculating deltas at the output stage, the delta vector would be m by 1. But then if we need to calculate the hidden delta, it would be m by 2 over here. But we are using the delta next. So imagine that we are in this case, we have m by 1. Then what exactly are we summing over? So we are summing over k, where we are keeping I fixed. Delta I. We are keeping I fixed, where I is the first delta I. Or is this for a single, these deltas? I'm I'm very confused whether the I here refers to the ith row, like the ith observation, or whether the I here refers to the ith element in a single row thing here. So these deltas take on the underlined formula around 5 minutes. Maybe I should have done that. Okay, so the audio is going to be really bad because the audio is going to be streamed. It's the matrix expression of the whole thing. Alright, I'm going to check it out. Maybe I should have done that in the first place, right? Hello, Andrew. So roughly 5 minutes.
I didn't prove it here, but you can actually, it's possible to prove if you know calculus that this expression is equal to mathematically the derivative of the g function.
Yeah, so it's actually really easy to show that. You just take the sigmoid function, you take the derivative, then you realize that the sigmoid function appears again. So you can just, it's like 1 minus that times the derivative with respect to the outputs.
Which I'm denoting by g prime. And finally, that's it. And there is no delta 1 term because I get. But I'll just tell you pragmatically what that means. What you do delta 3 is delta 3 is equal to theta 3 set as of that compute deactivate because proof that.
Well, I'm looking for the function.
Let's take everything and put it all together. These ij. Say for I equals 1.
Wait, I can't find it. Where is it?
To compute the error term delta, there's no delta. If you think of delta I,
Like, where's the formula?
Cross function. If you ignore regularization, then
5 minutes.
this term g prime of z3, that formally is actually the derivative of the activation function g evaluates pointed at the input values given by Z3. If you know calculus, you can try to work it out yourself and see if you can simplify to the same answer that I get. But I'll just tell you pragmatically what that means. What you do to compute this G prime, these derivative terms, is just A.
Oh yeah. That's just the whole data matrix, the whole delta matrix. Yeah, so the what you mean is that the A3 and the 1 minus A3 is exactly the same thing as the 1 minus A here. And then you have the theta prime times delta is exactly theta prime times delta over there. So, okay. But then why don't we just use this formula, or why can't we use this formula? Just theta prime times delta times g prime of that. Because so the dimensions. Wait, is it a matrix? Yeah, it's a element-wise multiplication, right? So let's see what the dimensions should be in the end. So delta should be m times features of the hidden layer. That's it. And then if we use the formula above, this is the delta. This is delta next. And delta next equals, let's write over here. So delta next is m by features in like one layer further, so to speak. And if we then do theta prime is exactly is the input node output node. So that's m times output, and then we have theta, which is output times input. And if we theta prime that, you get like, so if you have theta transpose, you get input times output. And then we have the A times A, which we can just do where A equals M times input, I believe. So can't we just fiddle around with this and calculate the delta matrix in one sweep? So imagine that we take like NP multiply 1 minus AJ. So that takes care of so that's going to be an M times input. This is going to be M times input, which is exactly this part. And then we do an element-wise multiplication. Then we do an element-wise multiplication of something that should also be M times input. And the only way we can get something which is m times input is where we just do delta times theta, I guess. So mp dot delta next times theta j. Mm-hmm. Okay. So let's see. I kind of want to copy this and paste it in here so we can look at both of the functions at the same time. You don't want to take the dot product. Why not? Dot product is just matrix multiplication, right? Because so let's print the delta next shape. Delta next shape. Then we can print the so the delta next shape, theta next theta shape, and we have the AJ shape. Okay, so if we run this, it's invalid syntax. Delta next is invalid syntax. In hidden delta. Wait a second. Alinton is saying you don't want to take dot product. Either that or you're using the wrong theta. Yeah, you should be using theta 1 here in hidden delta. Theta 1, theta 1, theta 1. 1 second. In hidden delta, you want to use theta 1. I'm not sure what you mean. I'm wondering why it's not running when you call the function. Oh wait, I forgot a comma there, of course. Be a comma here. Okay, so delta next shape is 4 by 1, which makes sense. Then theta shape is 2 by 3 and it's 4 by 3, okay? You should be using theta 1 here. Okay, I'm gonna quickly remove this. So we have 4 samples. We have 4 samples and or XOR. So this is your data. These are your targets. And then we print theta. Don't want to print theta. Samples and theta naught, theta 1. Okay, so this is correct. When you call the function, oh, you mean here, theta 1. Theta 1. Wait a second. So let's see. Let's remove all these print statements. So we take the layer 1 outputs, which is x and theta 0. Then we take the one layer output. No. So this calculates So layer 1 output calculates the new cost append cost function, sure. Delta output. Okay. And then theta 1. So this is basically this is your feed forward step. And then this is your back step. And then we plot it. So we first calculate the cost. So let's see if we can actually print cost. Let's see if we get there in the function. So we do have a cost, which is good. And then we are able to print out the shapes, which is also good. But then it errors because the shapes don't line up. So 4x1 and 2x3 are not aligned. Okay, so 4x1, which is of course the data. Wait a second. This is a typo. No, it's not. Wait a second. So let's print delta next, print theta j, and print aj. And print 1 minus aj. Alright, so this is, this is aj. aj, 1 minus aj. That's 4x1. Okay. NP multiply. Why do you want NP multiply there? Set to 0. Weight update. XW bias. Oh, you need an add bias in the A1. I'm gonna put it to full screen for a sec. Nope, still doesn't work. Oh my god, I can get so annoyed at that it's so slow. Oh my. I don't know why it's such a long notebook. It's really slow. Wait, so we are getting an error, but where are we getting the error? The error lies in trying to calculate. So the shapes don't match up. So we have delta next, theta j, np multiply, np multiply. So I know the multiply part works out, but so no wait, aj is 4x1. So this is no, wait a second. The shape of aj is 4x3. So this is a 4x3, 4x3. This is a 4x3. And you want, so this has to be a 4x3 as well. So that has to be a 4x3. So this thing has to be 4x3. So all we care about is that TMP is a 4x3. And it's not, or I can't see the size. NP multiply theta times delta next. Does that work? Theta times delta next? So 2, 3, and 4, 1 could not be broadcast together. Hmm. I'm rather convinced that this is actually correct because delta next, the size of delta next equals m times out, then theta equals out times in, right? Theta equals out times in. So this should, and then we have AJ, the shape is M times in. So this works out. Like, I'm kind of confident that this is correct. But then the error is in here somewhere. So we calculate the delta output, sure. Then we calculate theta 1. We add a bias to A1. I'm gonna have to look at the weight function again. So we take the I'm gonna have to look at the syntax again here. So weight update. We never tested the weight update actually, but that doesn't matter because the shapes don't matter yet. All right, so oops. So we add the bias to A1, we add the delta output, we add theta 1, and we add the rate. Then we print hidden delta, which does not manage to print. So we can actually so cost at iteration, Does this work? Not sure. It actually does. Okay, so cost at iteration not. Okay, and then it throws an error. But what? Okay. Are we done or not? Or is it still running? I think it's done. Shit. I should probably quit it. Ooh, it's learning. All right, so let's do this one more time. It keeps printing something. Because I print theta 1. All right, so there we are. We have results. Well, not sure if we have results, but let's put it at 50,000 or something. 5,000. I don't know. Let's hope for the best. Ah! Ooh. Ooh. Ooh, the cost goes up with training. That's a bad sign. So the cost going up during training is machine learning. It's like it's doing the opposite of learning. Okay, so use the old data not. What do you mean? Use the old data not. Let's see. What do we have? We have so weight update data use the old theta 1. Not 0, 1. So because in hidden delta, not the updated, yes. Wait a second. So hidden delta, yeah. Use the old theta 1, not 0, 1. But it says here. So we update the weights with AJ, delta next, theta j, rate. So this is theta 1, then this is A1, then this is the next delta, this is the rate. Then we have the inputs with the bias. Then we calculate the hidden delta. Wait a second. Why is this delta output? Hidden delta output add bias 1 theta 1 rate 1. What is incorrect? It looks to me. Wait a second. So Alinton is saying use the old theta 0 there 1 star star star. What do you mean? In the hidden delta, not the updated. So add bias A1. Theta 1, yes. Big theta 1. Yeah, this one. Not theta 0. So this one. This should be theta 1? Theta naught, theta 1, theta naught, theta 1, cost A2. Yeah, this is also machine learning, guys. Yeah, there's a slight delay in like there's like a slight delay. Use the theta 1 that hasn't been updated. Oh, like that. No, that's not true. You have to use the theta that you update, right? Or not, because otherwise your weight becomes different. All right, let's try, but I think it's a bit odd that you this should not like this is kind of a workaround, it feels. All right, let's make it 1,000 iterations is enough. Or 500 even. Oops. Let's say 500. All right. Let's see. All right. Okay. It's going down. It's not going down particularly fast, but it is going down. Oof. Runtime warning. Overflow encountered. That's a bad sign. Oh. Well. Okay, so this looks like something. Overflow encountered. What does it mean? Probably that it explodes. Maybe it doesn't converge. So let's put it at 50,000 and let's see what happens. Maybe my Jupyter crashes. Linton says, I have to raid. Good luck. Okay, thank you so much for joining in today. I appreciate it. Runtime overflow. Okay, so I'm just gonna fill in my super work and then I'm gonna call it a day. I didn't really I didn't keep a super work up for this session. I worked for 2 hours and 20 minutes straight, which is admittedly not healthy, and you should not do that. But I want to thank everyone for joining. Those who joined, what we did, we followed. This is an assignment from, I don't know, someone sent it to me. It's an assignment about neural networks, and you can build a neural network from start to finish, which is actually really cool. So we followed this neural network tutorial like almost to the end, and we just got a 2-layer neural network working by programming in backpropagation. So that is really cool. So we programmed in backpropagation, and then we gotta, hopefully we're gonna get a nice graph, but I'm gonna interrupt the kernel, and I'm gonna put it down to like just 1,000 to show you guys again what it eventually looks like. So this is what it looks like, which looks rather bad. Wait, maybe if I do it again. Maybe it needs a bit more than 1,000. 5,000. So it goes down, right? It's actually it goes down, but yeah. Okay. Anyway, on that note, I'm just gonna fill in my super work schedule. I want to thank all of you so much for joining in today. It was quite a calm stream, but it's nice as well. I worked for 2 hours 20 minutes straight, which is something I do not advise you to do. Please get up every 15 minutes or so to stretch your legs. I want to thank you for joining in, and I want to say have a good night. Thank you so much for joining. See ya.